Well, hello again, everyone. This is Mrs. Hanson one more time, wrapping up our Chapter 1 topics. We're going to talk about temperature and the three different scales we use to measure temperature, which would be known as the Fahrenheit, the Celsius, and the Kelvin scale. And when we do so, we'll just practice some conversion factors between them. First, let's define the term temperature, and it's a measurement of how hot or how cold an object is. Remember that that is very different from the term that we hear called heat. Heat is a type of energy, and it flows from a hot object from a cold object. And it's measured typically in a joule of energy in the metric system, or a calorie here in the English system. So heat is a type of energy, and temperature is the scale used to measure how hot or how cold something is at any particular point in time. So it's a scale, not a type of energy. There are three scales that we're familiar with called Fahrenheit, which is degrees Fahrenheit, Celsius, which is reported with units known as degrees Celsius, and the Kelvin scale. Notice there is no Kelvin degrees. It is just simply the unit called Kelvin. To convert from Celsius to Fahrenheit, we use the following formula. Fahrenheit is 1.8 times your Celsius degree plus 32. I'm giving you time to write that down. I want to convert a Celsius into a Fahrenheit. We use 1.8 times the degrees Celsius, add 32. Well, what if you were given Fahrenheit and need to go back to Celsius? So that would have us take Fahrenheit minus 32 and set that over 1.8. That just helps us reorganize each of those equations. And of course, to go from Kelvin to Celsius, Celsius to Kelvin, they're related by a factor of 273. So to convert between Kelvin, or from Celsius to Kelvin, we add 273 to the Celsius. And if we want to get back from Kelvin to Celsius, we're going to subtract out the 273. These equations we'll need to memorize in order to be able to convert from one to the other. So I'll just make a quick note. Know these conversions. Thinking about the comparison of these three scales. Here I have a thermometer that's given to me in Fahrenheit units. In the middle, I have a thermometer that's giving me Celsius units. And in the final, I have Kelvin units. Notice that the freezing point and boiling point of water. So water freezes at 32 degrees Fahrenheit. The other constant you probably know is that water freezes at 0 degrees Celsius. And that would be equivalent then to 273 Kelvin units. Water then boils at 212 degrees Fahrenheit, 100 degrees Celsius, and therefore it would boil at 373 Kelvin units. Since the freezing and boiling point of water on the Fahrenheit scale span 180 degrees, it has many more ticks between the degree marks, if you will, than the Celsius scale. The Kelvin scale is divided into 100 units, not degrees. But notice that the Kelvin and the Celsius have the same number of degree marks, whereas the Fahrenheit scale has many more degrees between each unit. Let's apply that. Let's think that through a little bit. Rank the temperatures from lowest to highest. We have 0 Fahrenheit, 0 Celsius, and 0 Kelvin. 0 Fahrenheit is below 30, right? Below the freezing point of water. Here's 0 Celsius and 0 Kelvin here. Which one is the coldest of all? Well, I see the bottom there, of course, is 0 Kelvin. Then we hit 0 Fahrenheit. Then we would hit 0 Celsius. So there's the order in which we have the coldest. And then over here would be the warmest of those three. An infant had a temperature of 104 degrees Fahrenheit. What would that temperature be in both the Celsius and the Kelvin scale? So let's do the Celsius first. The Celsius scale says I can convert that by taking the Fahrenheit, subtracting 32, and putting it over 1.8. So the Celsius temperature can be found by taking 104 minus 32 and dividing by 1.8. Will you hit that with me on your calculator and make sure I come up with the correct answer? 104 minus 32 equals 72. Now I'll divide by the 1.8 and I get 40. So 40 degrees Celsius. How about the Kelvin scale? Well, I know that Kelvin is found by taking the Celsius and adding 273 units. So the Celsius degree we just found, adding 273 to that, gives us 313 Kelvin units. 313 Kelvin. And we're right, 40 degrees Celsius, 313 Kelvin. Good work. You try some on your own, converting each temperature to the requested temperature scale, round to the nearest whole number, and then come back and check to see if we match. Let's try them out. Pause, don't cheat yourself. I'm always saying that, don't cheat yourself. Pause, do the work, and come back. Number 1, the Fahrenheit scale can be found by taking 1.8 multiplied by the Celsius and then adding 32. That means 1.8 times 20 degrees, adding 32. 1.8 times 20 is 36. Add 32 and we come up with 68 degrees Fahrenheit. Is that your match? That's rounded to the nearest whole number. How about problem 2? 150 degrees Fahrenheit to Celsius. So Celsius is found by taking Fahrenheit minus 32 and then dividing out the 1.8 conversion factor. So the Fahrenheit given to us was 150. We subtract 32 and divide 1.8. 150 minus 32 is 118. Now I'll divide that by 1.8 and we get 65.55. And round that to the nearest whole number, 66 degrees Fahrenheit. How about the third? A Kelvin to a Fahrenheit. Well, I don't have a direct road. I have to go Kelvin to Celsius to Fahrenheit. That's the conversion pathway. So Celsius is found by taking the Kelvin and subtracting 273. And that will give us a Celsius scale. And then from there, we see that Fahrenheit can be found by taking 1.8 times that Celsius and adding 32. So we have to use both of those equations. Step 1, 298 Kelvin minus 273 is going to give me the Celsius degrees. 298 minus 273 is 25. Then I can find the Fahrenheit scale by taking 1.8 times that Celsius we just found and adding 32. .8 times 25 gives us 45, and now I need to add 32 to that. And I found 77 degrees Fahrenheit. And the fourth one, oh, I can come down and give myself room. The fourth conversion, it looks kind of simple, so I thought I'd give myself room for that. 75 Celsius to Kelvin. I'd want to know Kelvin, and that's found by taking Celsius plus 273. So that Celsius degree of 75, adding 273 units to that will give us the Kelvin units. 75 plus 273 is 348 Kelvin units. Our last topic is on density and specific gravity. With our density, we are going to define the term as a physical property. Remember that term from the earlier part of our lessons? Physical properties. Those are properties or adjectives that can describe a compound without changing its identity, right? So a density is a physical property that relates to the mass of a substance and its volume. Its formula, density, is found by taking mass, measured in grams typically, divided by volume, which is measured in mils or cubic centimeters. That's what CC stands for. But we need a mass over volume unit. So as we practice, I often like to use these little algebra helpers, and I'm going to call this a round little buddy, or it's just a formula tool. I'm going to do so by drawing a circle. Do that with me on your note page, and cut that circle in half, and then cut the bottom into half again. So we have a diagram that looks like mine. So here I have mass on the top, and I want you to place density in the first quadrant here and the term volume here. Mass is measured in grams, volume in a milliliter, and so density is a derived unit, gram per mil. Now the reason I like this is that it allows me to quickly find the variable in just an algebraic form to know if I'm going to be multiplying or dividing. Let's suppose I want to solve for mass. The unit I want is mass. So with your finger, if you would, cover the term mass. Just cover it up so you can't see it. Pretend that highlighter is your finger. And now what do you see? I actually see the formula of how I'll solve for mass. I'm going to hit density times volume to find mass. Suppose, for instance, instead of wanting, let me just put that back. Let's suppose instead we wanted to solve for density. And if I cover my finger and say that this is highlighted, I want to solve for density, cover that so you can't see it. Pretend my highlighter is my finger and I'm covering up the term density. Do you see how I find density then? It's going to be the unit mass over the unit volume. The last variable, let me just quickly erase that density term. I don't want to highlight that anymore. And I'm going to just quickly rewrite it. And let's suppose now I want to highlight, and I'll make this one in blue, I want to solve for volume. All right, so that's the variable I'm trying to solve for. Cover that up with your finger. Cover it so you can't see that part of this diagram. And you now find how to find volume with this formula. I see that it's mass over density. So by highlighting or covering the unit you want, you're staring down the algebraic form of how to pull it out of this variable. All right, so it's just a little tool to help us practice. Let's jump in. If a urine sample has a mass of 211 grams and a volume of 209 mils, what's the density of that formula? Our round little buddy. I know that density is defined as mass over volume. The mass is given to us as 211 grams. The volume is given to us as 209 milliliters. I want to know density. So keep in mind, our round little buddy says the unit that you want is the unit that you cover up. And when you cover that up, you find the algebra of pulling out the other variable. So in the round little buddy, I just placed the numbers that were given to me. I had 211 grams as the mass. That's the top of the circle. I was given a volume of 209 mils. That's the bottom right of our circle. So I can clearly see to find density, I'm going to hit 211 grams divided by 209 mils. And when I simplify that, 211 divided by 209, just hitting that on my calculator, you do the same. We get a value of 1.0095, and it goes on from there. We need 3 sig figs. The number that we're going to drop first will round up. So 1.01 grams per mil is our density. Pretty cool. Try another with me. Calculate the mass in grams of 15 mils of a saline solution that has a density of 1.05 grams per mil. Here's our strategy. Let's get our round little buddy ready. I know that mass goes on top. I know that volume goes in the bottom right. And I know that density goes in the bottom left. The mass is what we're solving for. The volume given to me was 15 mils. The density given to me was 1.05 grams per mil. Now, think about this round little buddy and how to use it. The unit I want gets covered up. I want to know mass. And when I say cover it up, pretend that highlighter is my finger. And what formula do you then see? I see that mass can be found by taking the density times the volume. So I'm reading straight across. If they're across from each other, that means times. If they're on top and bottom from each other, of course, that means divide by. That's how we're reading this chart. So the density of 1.05 grams per mil times 15.0 mils. Notice how that cancels the volume and you're left with a gram. So I'm going to hit 1.05 times 15, and my screen says 15.75 grams. We're allowed 3 sig figs, so this number will need to be rounded up, 15.8 grams. These are fun. They're kind of easy, especially after coming off conversion factors. Calculate the mass in grams of 10 mils of diethyl ether with an anesthetic that has a density of 0.713 grams per mil. I know that mass goes on the top, density is the bottom left, and volume is the bottom right. Calculate the mass, so that's my target variable. I'm given 10 mils and a density of 0.713 gram per mil. Cover the variable with your finger that you want to solve for. We want mass. So therefore, I can see the formula will be mass can be found by taking density times volume. 0.713 grams per liter times 10 mils will give us our gram. I forgot that little m there for milliliter. That bothered me. Thank you. 0.713 gram per mil. 0.713 times 10. And you get 7.13. And that has the proper number of sig figs, 3 of them. Want to do another? If a household recycles 10.5 kilograms of bottles composed of PET in a month, and the density is in a gram per mil, what volume in liters does this represent? So here I'm saying units are not matching. As I was reading through this, I noticed that density was given to us in a unit called 1.38 grams per milliliter, right? So grams per mil. But they gave us kilograms for the mass, and they gave us a unit that we wanted, liters. So we have to convert this into kilograms per liter in order to come up with the correct ratio. This is easy enough. I just wanted to point out that the units aren't matching. I know that in a gram, there are 1,000 grams in every kilogram. Remember how kilo means 1,000? And I know that milli is 1,000th. So there's 1,000 milliliters in a liter. And when I do this, I'm converting out grams into kilogram and a milli into a liter. So if I hit that out, 1.38 divided by 1,000, I want to move the decimal place 3 spots to the left. You get 0.00138 kilograms. And you want to take 1 and divide it by 3 spots. You're going to go 3 spots to the left, 0.001 liter. Now, why did we do that? I want to make sure the mass and the volume match the units that are in density. So, for instance, in our round little buddy, 10.5 kilograms was the number given for the mass. It's going to be on the top of this round little buddy. The density is now given to us as 0.00. We want to simplify that. Let's do that. 0.00138 divided by 0.001, and it comes out 1.38 kilograms per liter. That's much easier than having that ratio in there. That's our density. And so now you can see the volume will be a liter when we solve. Volume will be found by taking the mass over the density. And remember, that's that little trick where we said cover the unit that you want. We want to solve for the volume. Cover it with your fingers. You can't see it. And that shows you the algebra of how to pull out that variable. Mass is on top of volume, so that means we're going to divide. We're going to divide 10.5. Oh, my screen is just acting up. Let me fix it here. We're going to divide 10.5 kilograms set over 1.38 kilogram per liter, and our answer will be in the liter unit. 10.5 divided by 1.38 is 7.6. How many sig figs? 3? 7.61 when I'm done rounding. The screen says 7.608 and on, so 7.61. That was a good one to practice with, wasn't it? The term specific gravity is very much the same as density. It's just a comparison of a different substance's density to that of water. We know that water has a density of 1 gram per mil at 4 degrees Celsius, so 1. So what's really interesting about specific gravity is just turning a density unit into a unitless number because it's comparing it to the specific gravity of 1. So the units cancel. The units in the numerator, which is the top number, cancel with the denominator, which is the bottom number. If I have a gram per mil set over a gram per mil, they just simply cancel. So specific gravity has no units. It is a unitless quantity. The specific gravity of urine, for example, is measured to check if a patient has an imbalance in their metabolism. If a normal urine range has a density in the range of 1.003 to 1.030 gram per liter, notice it has the exact same specific gravity range because we're simply comparing these numbers to that of water. Those units cancel and you've converted density into specific gravity. The exact same number, but no units. This consistently high or low levels can indicate an imbalance in your metabolism, indicating perhaps the presence of diabetes if your large glucose levels are over a span of time. So our last slide. If the density of a liquid is 0.80 grams per mil, what is its specific gravity? Well, the specific gravity is a unitless number. It is 0.80. That's it. And if the specific gravity of a substance is given as 2.3, what's its density? Well, it's 2.3 grams per liter, the density unit. Now remember, when we defined that gram per liter or gram per mil, it doesn't matter what unit you put on there. So it says, since this was gram per mil, we'll report that out as gram per mil. We just need a mass over volume. The density of water is 1 gram over 1 milliliter. So 1 gram over 1 mil. If I divide 2.3 grams per mil over 1 gram per mil, we come up with a specific gravity, 2.3. So the exact same number with no units for specific gravity. I am so proud of you for making it through your first chapter set of lessons. You've completed the note pack at this point. You want to wrap up kind of getting it all finalized, taking pictures with your CAM scanner app and submitted a single document, multiple pages long, but one document into your Dropbox by the assigned due date. I look forward to working with you in Chapter 2. Hey, don't forget to email me if you have any questions. I'm here to help support your learning.